Hola, people of the big wide world. We are back here to understand the semi-classical model of light-matter interaction. And in the last video, we saw what happens when the light field is exactly tuned to the atomic transition. And we saw the effect of Rabi flopping, in which the atom is constantly going to the excited state and back to the ground state sinusoidally in a coherent manner. And I ended up the video saying that we were now going to see what happens in the nearly resonant case, and I just wrote the math here already because it's a bit more math, but in terms of the insights of the physics that is behind, is a very similar scenario. So I will guide you through this math. It's not very complicated. The idea here is that now we consider that the detuning is not zero, but the detuning is not crazy enough, in the sense that if the detuning is too large, then the approximations we made for the two-level approximation of the atom and the rotating wave approximation, they break down. So the equation should be different. So that's not the case that we are considering here. So that's why we say that the detuning is not zero, but we are still close to the resonance. So it's nearly resonant. Otherwise, these equations don't hold. So if one writes down the equations for the coefficients that we saw in the last video, for the two coefficients of ground and excited state, and one do again another derivative with respect to time to decouple them between each other, one arrives to two equations. This here means that it's a very similar equation for the CE, for the excited state. Let's focus on one of them because the other is exactly the same. So the ground state, for example, one gets a second derivative with respect to time, then a term that now is not zero because the detuning is not zero, derivative with respect to time, and then another dc term if you want, an omega squared over 4. Now solving these equations is just a mathematical problem, and they are easy to solve if one realizes that this operator here, this entire operator, can be written as the product of two different operators that only have one derivative with respect to time, so it's easier to solve. So this is the operator, and here it's very easy to see that the solutions that we should propose are, again, not very surprisingly, oscillatory solutions, because one has a derivative with respect to time and then a pure imaginary term on the coefficient. So is the derivative of the function that is an imaginary thing times the function, so probably the solutions are going to be exponentials that are imaginary, which are oscillatory terms. So that's why if one looks at solutions of this way, one can write the general solution as exponential, imaginary exponential, and then some cosine and sine for the omega. Now, one thing that is very important is that in order to do that, in order to have this step here, to write this operator in terms of the product of these two operators, one realizes that now what we call the Rabi frequency omega now is going to be a square root of the Rabi frequency that we had before plus the detuning that is non-zero now. If the detuning is zero, then this omega tilde that I defined would be exactly omega, and that would be the Rabi frequency. But now these oscillatory terms, they go with this omega tilde. So the frequency of the oscillation changed. And this omega tilde is called the generalized Rabi frequency, for obvious reasons. Then another thing we can do is, instead of writing the solution with these coefficients here, A and B, we can write it in terms of the more practical initial condition for the atom. And when one does this, we arrive to the conclusion that the solutions are of this type. This is the solution, for example, for CG. I will leave a PDF with all the equations well written in the description if one is interested in looking at the math in more details. But the idea here is, again, we have an exponential that is imaginary, and then we have sine and cosine functions with this frequency omega tilde and with some prefactors here. And now let's put an example to see what happens and what is the difference with the resonant case. It's very similar, as I told you before. So the example that I'm gonna get here is exactly the same as the one we got in the last video, which is we initially start with an atom in the ground state, we shine the light, we see what happens. or what is the prediction of this model. And so if we do that and we plug this initial condition into this equation, we get these other equations. As you can see, for example, this the equation for the excited state is pretty simplified. And if we calculate the probability of the atom to be excited as a function of time, which is just the modulus square of this function, we get this this reduced equation, in which we can see two things. The first thing is, as I anticipated, the frequency, the new frequency of oscillation is the generalized Rabi frequency and not the bare Rabi frequency. That is a frequency that is higher than before, because the generalized Rabi frequency is square root omega square plus delta square, which is always bigger or equal than omega. So it's a faster oscillation than before. And the other is that the amplitude of the oscillations is reduced, because this thing here is omega square over omega square plus delta square. So as the detuning is increased, the amplitude is smaller, the amplitude of the oscillation. So this means that if we plot here the probability as a function of omega t in this axis, this dashed line is what we had before in the resonant case, which is an oscillation that goes from 0 to 1. And now, as the detuning is non-zero, they still oscillate, but they oscillate faster and with a lesser amplitude. This you can understand physically as simply the fact that since the laser is not tuned exactly with atomic transition, then the atom, if you want, quote quote, sees less the light, so that the probability of the atom to be excited reduces. And this is what we see in this equation. For example, for the red curve, we can go to an extreme case in which or a more extreme case if you want, in which the detuning is larger, is 5 times omega, capital Omega, the Rabi frequency. And in this case, the oscillations are very fast, which is this case here. They are very fast, but they are also almost nothing in amplitude. So the atom is almost not seeing the light, it's seeing a little bit. And this is the physics of what happens. This case is a more general case. If we take these equations and we plug the detuning equals 0, we will recover the resonant case that we saw before. But they are more involved mathematically, so I think it's nice to see them, both cases, independently. But now let's see another effect of this light-matter interaction that is related obviously to what we just saw in the dynamics, which I call it the avoided crossing. Avoided crossings are a phenomena that happens commonly in quantum mechanics when you start mixing states, and you will see what I mean by that in just 1 second. So the idea is the following. The states, ground state and excited states, these states here, are eigenstates of the atom, right? Because we define them literally to be the two levels that diagonalizes the Hamiltonian of the atom. So if I apply, for example, the Hamiltonian of the atom on the excited state, then I will get the energy, that in this case is this energy splitting, because we said that the energy equals 0 corresponds to the ground state, and this was omega 0, times the state itself. It's an eigenstate of this state. But now one could ask, okay, what are the eigenstates of the new system? So now that we have the Hamiltonian, which is the Hamiltonian of the atom, plus the Hamiltonian of the interaction, what are the eigenstates of this new system? So we can diagonalize this Hamiltonian, and what we will get is that the Hamiltonian of the system can obviously be written as a certain superposition. So it's a superposition of the ground state and the excited state. But one can calculate what is this superposition in particular. So what are the new stationary states of the coupled system for the atom? These states, by the way, sometimes they are called dressed states, but we will call them dressed states when we go to the full quantum picture, when we also quantize light, because there is clear why they are dressed, because then, well, you will see. I'm not going to spoil anything. It's a cool concept. But the idea is the following. Okay, let's diagonalize this Hamiltonian. Now, a little detour. For diagonalizing this Hamiltonian, it's nice to do the following. It's nice to take the Hamiltonian in an easier way. So if you remember, the Hamiltonian of our system was h bar omega 0, then we have the projector on the excited state, and then we have h bar capital omega divided by 2 sigma e to the minus I omega t plus sigma plus e to the I omega t, something like that. And now diagonalizing this Hamiltonian is a bit annoying because of this explicit time dependence. But we can get rid of them. We did that for the coefficients, and I said that this was called transforming into a rotating frame that was going with omega, with this omega here. Now if we want to do it with the operator, what we can do, and this we will do a lot in the lectures, is apply a unitary transformation. In particular, let's say that we want to apply this particular unitary transformation, E, to the Hamiltonian. Then one would follow the rules of what is the new Hamiltonian after the transformation, which is basically this. One has also IH bar derivative with respect to time of U daga. This term here, this I will show you probably why this is the case, why the transformation of the Hamiltonian is like this. It's easy to show, but it's just for the matter of simplicity, not doing a big detour. Let's do it in another video. Just believe me here that it will be proven. It's easy to prove. And this term is because the unitary we are actually considering right now is explicitly time dependent. But when you do that, and when you apply this transformation, we just apply the rule for operators and so on. We will again do a lot of this in a video that is not going to be very far in the future, in which we will consider the dispersive regime of circuit quantum electrodynamics, but I don't want to spoil you again. If you just apply this transformation right now, one gets the following Hamiltonian. One gets now the detuning here. Before it used to be omega 0, and now one just removed the time dependence. And this is very nice because now this Hamiltonian, if you put it in, well, if you put it in matrix form, it has the following matrix form. Right? Because this EE is this term here, so it's minus h bar delta, and then these are all of diagonal terms that are the same. So this Hamiltonian is easy to diagonalize, and in particular, let's diagonalize this Hamiltonian, which means that we are gonna do minus lambda, which is the eigenvalue, omega divided by 2, omega divided by 2, minus delta minus lambda, this times h bar. This should be equal to 0. And now, well, this is lambda times lambda plus delta minus omega over 2 squared is equal to 0, and one can solve this equation for the two solutions for the eigenvalues. There are two solutions because it's a 2x2 matrix. And if one does this, one gets the eigenvalues that I call lambda plus minus, but I'm gonna actually call it the energies because these eigenvalues are the eigenvalues of the Hamiltonian, so they are the energies, which are minus h bar delta divided by 2. And you can show this, maybe you can do it if you're interested your own, it's a good exercise. H bar omega the generalized Rabi frequency divided by 2. And these are now the new eigenenergies of the coupled system. But one can also calculate the new eigenvalues. Sorry, these are the new eigenvalues. One can calculate also the new eigenvectors, so the new eigenstates. And for doing that, one, well, just to recall, I'm not gonna do it, but just to recall, one would do the Hamiltonian applied onto one state that we call it A and B, which is the eigenstates, should be equal to this energy, the plus or the minus, applied on the eigenstate. And this gives a system of equations that one can solve, apply the normalization for A and B, sorry, and then get the eigenvectors. I will write just the solution of these eigenvectors. Again, this is a good exercise if you want to do it on your own. But the idea is the following. One gets that one eigenvector that we call plus is the sine of some angle that I will define now, g, plus the cosine of some angle, e, and the eigenvector minus is the cosine of this angle minus the sine of the angle. And now this angle is defined such that the tangent of this angle twice is equal minus omega divided by delta. And this angle goes between 0, is defined between 0 and pi over 2. So one can realize the following. If the detuning is 0, then the tangent is infinity, which means that the angle inside tends to pi over 2, and in that case the plus state is exactly an equal superposition, because this is twice, so you would have that actually this is pi over 4. So one gets exactly an equal superposition of G and E when the detuning goes to 0. And this means that when the detuning is 0, the states are maximally mixed. So the light is maximally mixing the ground state and the excited state. And these are the new eigenstates of the system. While it is also the case that when the detuning is very large, so if the detuning is very large, it tends to infinity, then the angle tends to 0, and in this case, if the angle tends to 0, the sine of 0 is 0, and the state plus is just the excited state, and the state minus is just the ground state, which is a way of saying, if the detuning is very large, then the light and the atom, they don't see each other, they don't want to talk with each other, they are angry between them, and so the atom just goes by itself, it doesn't see the light. And the eigenstate of the atom are exactly these eigenstates, excited and ground state, so he doesn't mix with itself. Alright, but now we can see the following. We can plot, here we have the detuning, and as we change the detuning we can plot these eigenvalues, E. So we'll change color here. So imagine that omega is equal to 0. So there is no coupling between light and matter. So then the eigenstates are trivially, we'll write them, E plus minus, they are trivially minus h bar delta divided by 2 plus minus h bar delta divided by 2, because remember that here we used to have omega, but if this omega is omega squared plus delta squared, so if omega capital is 0, this is just delta, and that's why we recover a delta here. So this means that the excited state, which is this one, is linear with the detuning, while the ground state is always 0, because we put the energy of the ground state to be 0. This will be the energy of the ground state, that is equal to 0. And the energy, well, just to be clear, the energy of the excited state is minus h bar delta. Alright, but now what happens when we turn on the interaction? So when we turn on the interaction, we can play the same game and plot the energy as a function of the detuning, and now what we see, if you just plot the eigenvalues, when we get something like this for the excited state, which again is just this energy, just to be explicit, is minus h bar delta divided by 2, and then minus, in this case, h bar divided by 2 square root omega square plus delta square. So there is a parabolic behavior, that's why these curves. But then the ground state does the opposite, right? And we can write here an asymptote, because when the tuning is very large, the energies coincide. This should happen. Sorry for this, but this should go through the origin. Sorry for this. This is supposed to be a straight line. Let's put it like this. Yeah. But now this is the phenomenon of the anti-crossing, because now the energy difference here, this new splitting, is omega. So what is happening here? Both states are exactly the same energy. So the ground state and the excited state, when the detuning is 0 and there is no light, they are exactly the same, which is normal because the detuning is telling you the splitting. So there is 0 splitting at 0 detuning, but this degeneracy is lifted by the presence of the light. So the light is lifting this degeneracy and is mixing up the eigenstates of the system, the original eigenstates of the system. And this is called a crossing because now it's important to notice that here this would be the excited state and this would be the ground state. But when we go to the other side, this, in the limit that we go very far away in the tuning, this is actually the ground state of the system, and this is actually the excited state of the system. So the presence of the light is switching. There is an avoided crossing in the middle. And this shift of the degeneracy with an energy that is exactly the Rabi energy, if you want, so the Rabi frequency, this is called the AC Stark shift, or it's also called sometimes the lamp shift of the atom. And this, it will appear and it will be even more clear in the full quantum mechanical case, because here we are focusing on what happens to matter, to the qubit, in the presence of classical light. But now, if the light is also quantum, we can also ask the question, what is happening to the light? But we will see in the future. But it's very nice that a model that is relatively simple, with a qubit that is coupled to classical light, already gives you a little model to understanding this type of phenomena of lifting degeneracies, avoided crossings, that are very important in the field of quantum electrodynamics and in the field of atomic physics and ultra-cold atoms. It's a feature phenomena of quantum mechanics that appears from the actual nature of the theory itself. So it's more profound than one would think. And I think that's very interesting. Also, for free, we actually calculated the eigenstates of the system in the coupled system. This angle, by the way, is sometimes called, or I don't have it written here because it's a weird name, but it's something like Stuckelberg, the Stuckelberg angle, in honor of one physicist that was a pioneer in this type of field. And now finally, following this anti-crossing line, let's see one nice effect that is called the Landau-Zener crossing, studied obviously by Landau and Zener in the 50s. So suppose that we have an atom in the ground state and we want this atom to become excited. What could we do? So one of the things that I told you in the last video is that we can send a pi pulse. We can send a pi pulse with a certain duration, type pi, such that, wait 1 second, sorry for this, little technical problem here. Alright, sorry for that. So we can send a pi pulse, so that if the time is good, so if the time is such that omega t equals pi, then we get exactly this transition. But now this is not sometimes the case in atomic physics, because this is an idealized scenario. We are not considering that the laser has a certain frequency omega, but it has a certain jitter of the frequency, so there is phase noise, amplitude noise, and this will affect exactly what is the pi pulse that we would need, because then the tuning has a certain error as well. And for the matter of being precise, the transition of the atom is not sharp. Sometimes it has a certain line width. So all of this makes this not to be perfect. But there is a way to, even with experimental imperfections, actually make this transition perfectly well, and it's by sweeping the laser frequency, so sweeping omega over the transition. So if this is omega 0, we start, let's say, here with a certain detuning, and then we sweep this omega along the transition, and we have to sweep this omega sufficiently slowly. So the procedure is the following. Imagine that we start with a certain delta that is way smaller than minus omega. So we start on the left here, on the left of the transition. So delta is negative. Okay, and now you can imagine that we have this. I just show you the energies. These are the two energies for the excited state and the ground state in the presence of light, and we are starting in a point here. So this is delta, we are starting a very small delta. So this means that the state of the system is basically the ground state, right? So the light is so far detuned from one side that the states are not mixed. But now you start sweeping frequency, and in particular you start increasing the frequency. So you go in this direction. As you go in this direction, the state of the atom will start mixing, right? But if you do it slowly enough, you do what is called an adiabatic passage, and the state will follow the state of the line. So what you are doing is you are following this curve here. You are mixing and mixing the state, in the sense that you are changing the angle theta. You are increasing the angle, the Stukenberg angle that we said before. So you are mixing more and more the excited and the ground state, but you are keeping the state in an eigenstate of the system, because again, remember from quantum mechanics, if you are in an eigenstate of the system, whatever it is, the system wants to remain in this eigenstate of the system unless there is some big perturbation to it. So if the perturbation is very small, by the adiabatic theorem, you know you are going to continue in this eigenstate. So you are going to continue through this line. And this is the concept here. You are not going to jump. But here, if we go to the other extreme, because when we go to the tuning 0, the states are completely mixed. But when you continue doing that, you arrive at a point that you are here. And here at the end of this line, as I told you before, because of the avoided crossing, now the minus state is actually the opposite, is actually the excited state. So when you stop there, what did you manage? Well, the atom, just from the point of view of only the atom, made exactly the transition ground state to excited state. And some people, they call this transition in this way the Landau-Zener transition. And now, the question that Landau and Zener wanted to solve is, how slow should I go in order for this transition to be efficient? Because if the sweep is too fast, then the qubit can tunnel through the avoided crossing, can actually go through the avoided crossing, because then you just have a Fermi golden rule that tells you what is the probability of actually changing the eigenstate when you are perturbing a system, because in the end we are perturbing the system by changing the omega. In other words, now omega, that before it was just a number, now depends on time because we are sweeping omega over time. So this means that when we wrote before a minus I omega t, for example, now we will have something like minus I integral from 0 to t of omega t prime dt prime. Omega at a certain time t is called the instantaneous frequency. And the fact that omega depends on time sometimes is called a chirped phenomenon, or you have a chirped pulse. It's pulse in the sense that now omega will have a time dependence. Alright. So now the Hamiltonian of the atom in the rotating frame would be minus h bar delta of t sigma plus sigma, and the Hamiltonian of the coupling would be h bar omega divided by 2 sigma plus. This didn't change. The Hamiltonian of the coupling is the same. We are just moving the frequency. Obviously, the tuning now depends on time because this is omega t minus omega 0. Okay. So now one can play the same game and we can write down the equations of motions for the coefficients. So let's try to solve the system in this case when omega depends on time. For example, one would get that the second derivative with respect to time minus I delta dt, and this is exactly the same equation as the near resonant case, but now delta depends on t. And now one has a new coefficient, which is this one, because now delta depends on t, so there is some derivative of delta with respect to time, is how fast, which is what we are interested in, how fast we are changing this detuning. This applies on C, for example, is equal to 0. And you have a similar condition for the CG. In particular, if you want to derive it yourself, or if you want to see the notes, minus I delta t derivative with respect to time plus omega squared over 4 CG equals 0. And these are now the equations of motion. And now it becomes a little bit more technical, mathematical. In order to solve this system, one has to transform yet again to another frame. So here we just make the following change. CE prime is CE tilde e to the minus I over 2 integral from 0 to t of delta the t prime dt prime. And then also let's consider that delta the t is equal to alpha times t. This means that we are linearly sweeping the frequency, which is a very reasonable assumption, it's a very reasonable thing to do. So it's a linearly chirped frequency. Okay. So now we can substitute these C primes into here, and we can consider this delta, and we will arrive to some other set of equations. So the equations are the following. The second derivative with respect to time plus omega squared over 4 minus I this alpha, but remember this alpha is just the coefficient here, is how fast we are sweeping linearly the frequency, plus alpha squared over 4 t squared, all these thing CE prime, this is equal to 0 for the new coefficient, and something very similar for the other coefficient. Just realize that here we are just doing some math. We are, physically speaking, we are not doing the same. We are in the same exact situation, except from the fact that we were said that we will sweep the frequency in a linear fashion. But apart from that, that's why we have this alpha. The rest is exactly the same. CG prime is equal to 0. And now these two equations, they are really harder to solve than the equations that we saw before. Differential equations are characterized by that. If you have ever worked with differential equations, you realize that there are some that we can solve, and there is a very big majority, 99.9% of them, that you just change a little bit the differential equation and it becomes very, very hard to solve sometimes. And sometimes not even with analytical solutions. In this case, there is a way, and there is another transformation. I'm going to write it for the matter of completeness, but it's not really important for the argument we will make, but I want to show you that if you do now another transformation, which is calling new this I omega square over 4 alpha, and calling z e to the minus I pi over 4 square root alpha t, then if you apply this, you get two equations that are simpler, but most importantly they are the form of some equations that are differential equations that are well known, which are called the Weber's equation. So you get something like that. Here is z minus z square over 4 over c e prime is equal to 0, and then something similar, you will get the derivative with respect to time. Here obviously I'm skipping the mathematical details. If you want to see them, you can see them in the notes, or in some books you can look for it. Cg prime is equal to 0, and these are called the Weber's equation. These are in this form, and we know the solution to this equation. Well, Weber derived the solution for these equations. The solutions for these equations, they are called parabolic cylinder equations. Parabolic cylinder functions, sorry, not equations. Like Bessel functions, but just another family of functions that usually are denoted d nu of z. We will also have d nu of minus z. This would be the solutions for the c prime. And then we will have d of minus nu plus 1, the iz, and d of minus nu plus 1, the minus iz. So the idea here is that we can compute the solutions for the coefficients, so we know the dynamics of the system while we are sweeping the frequency. So we will know what happens to the atom, because we want to at the end understand, or this is what Landau and Zener wanted. They wanted to understand how this passage from the ground state to the excited state in the presence of this chirp was done as a function in particular of this alpha, of this speed of the transition. Okay, so here these equations can be analytically written, but they become very, very, let's say, they become involved. So under some approximations, these equations are basically of the form a d nu plus 1 minus iz. This is, I know, a little bit more dark that I passed from this to here. I just wanted to let you know that there are these equations that are parabolic cylinder functions, and then under some cases, because it gets, we start having a lot of parameters, this alpha, this the tuning, so under some specifications we can actually write down, we can actually plot what is happening already if we plot just the solutions. But physically speaking, it's very nice to see that under some conditions these coefficients here, the excited state coefficient becomes this function, where this a, where this parameter a, the modulus of this parameter a is a square root modulus of this nu, that again is this thing here. So it depends on the ratio between omega and alpha, which is the actual thing that will interest us, and then minus pi modulo of nu divided by 4. We have some conditions to arrive to here. For example, I will just let you know that we have to write the solution for the Cg prime, and then apply that when we know that when t goes to infinity, Cg goes minus infinity, then Cg goes to 1, because we know we start from the ground state of the atom, and then we sweep the frequency, remember. And we also know the opposite, right? The Ct, when this goes to minus infinity, this tends to 0. Alright. So then, because of this solution, one can argue that when one calculates the probability of the atom to be in the excited state as t goes to infinity, t goes to infinity means that delta goes to infinity, because omega is going to infinity. Infinity is a mathematical way of saying that it's very large. So you started here, let's say, with a certain delta, then you crossed the transition, omega 0, and then you are really going farther away. So what is the state, the stationary state at the very end? This is this probability. And this probability one can show, and Landau and Zener did show, that is 1 e to the minus 2 pi modulus of nu. So this means that if nu is very large, then this probability will tend to be 1. Or in other words, let's write it in the following way. The probability that we are not in the excited state after this sweeping of the frequency, so let's call it the probability of not excited state, let's call it like this, is 1 minus the probability of being in the excited state when t goes to plus infinity, which we just wrote down here, so it's exactly e to the minus 2 pi nu. It's exactly this. And this is the result of Landau and Zener. And now this nu, just recall the modulus of nu. Well, if you want, let's write it literally. So this probability of not excited, if we write it in the terms that we wanted, is the exponential of minus pi omega square divided by 2 alpha. And again, the precise details of the mathematics, I know I skipped a little bit, but because it would become very technical, and you can look at the math if you want in detail. But the idea here is the following, that the thing that we care about is omega square compared with alpha. Again, alpha is how sweep we are linearly changing the frequency. So you can think about it as this is the frequency over time. So we have something like this. The alpha is this slope. So it could be very fast. And if it is very fast, what happens is that this is big, so this starts to be 1, so the probability of not being excited is actually very large. So if you go very fast changing the frequency, in the limit of time goes to infinity, you don't arrive to the excited state. You go back to the ground state. While if you go very slowly, then this alpha is small. If the coupling is also big, which also helps you, because again you have to compare omega with alpha, then you can actually make the transition and do the Landau-Zener crossing. And so, just for showing you how this looks like, we can plot using the parabolic cylinder functions that I showed you before. This is delta, so this is delta equals 0. This is delta over omega, this is, let's say, 20, and this is minus 20 as I wrote it here, and this is, let's say, 1. And so you start, imagine for example that alpha divided by omega square is of the order of 0.2, and here I assume some values, right? It doesn't really matter. The thing is that it's gonna be a small value. Then what you see is that you start at 0, so the system starts being in the ground state, and then when you actually calculate this more complicated parabolic cylindrical function, you see some oscillations, and at around 0 the probability goes up. It oscillates a little bit here, and then it tends to just remains at 0. So this is exactly what we wanted, but this is analytically proven, and this is a very nice mathematical way of solving the problem, right? Because you gain all the insights of physics. While if alpha divided by omega squared is, let's say, of the order of 2, so it's 10 times higher, then you also start at 0, this is fine, then you continue at 0, and then what you see is that it increases the probability, but then it oscillates, and at the very end it oscillates towards a value that is not 0. And in particular, this thing here from 1 is this probability of not excited state that we said before. And this is the Landau-Zener crossing. Now, a note that we should make here, just to finish this video, is that the velocity at which we change is true, it should be smaller than omega squared in order for the transition to be prepared well, but it's also true that we are assuming implicitly that this is bigger than the T1 of the atom. The T1 is the relaxation time, because we are assuming here that the atom, when it goes to the excited state, it goes from the ground state to the excited state, it will remain there. But this is not true, because there is a thing called spontaneous emission that will make the atom to go back. It's a source of decoherence that we will talk about decoherence a lot in future videos. What happens when we open the system and it's an open quantum system. But for now it is clear that the time that it takes, if I take the atom, I put it in the excited state, I just wait, the mean time for the atom to go from the excited state to the ground state to relax, this time is called the T1 time of the atom. And obviously, if you are sweeping the frequency very slowly, if it is too slow, you are giving the atom the time to relax, and so this will never work, because it will relax to the ground state, and then the probability of it to be in the excited state is 0. So this Landau-Zener crossing only works under also the condition that is, you do it sufficiently slow that you don't create tunneling effects through the minus state, so you don't create a big probability of this to occur while you are sweeping the frequency. Remember, these are the eigenstates of the coupled system. But at the same time, not so slow that the atom has time to relax. So it depends already on the specific system that one has. And with this, I think it's a good time to stop the interaction in the semi-classical model, because we got a good insight about how is light-matter interaction in this semi-classical model. We saw the resonant case, the Rabi flopping, we saw what happens if you are not exactly tuned to the atom, we saw the avoided crossing that it appears, and we also saw the Landau-Zener crossing that one can perform. There are more things that one can say about the semi-classical process, semi-classical model, and we could generalize it to more than 2 levels. For example, considering 3 levels already, you will see that the complexity of the system is increased quite a bit, even though there is only 1 level more. But I think that it's worth it now, and in the next lesson we will see what happens if we also quantize light, right? Because I think this is also a very important question. So in the next video we will change gears in some sense, and now we will have an atom or a qubit, if you want, with a ground state and an excited state, certain splitting. But now we are going to couple this to a quantum harmonic oscillator, so a photonic cavity. So now we will have also individual states with a certain number of photons, and we will couple these two. This, what I mean by that is that we quantize light. So now the electric field will be an operator. And we will see what is happening between the two and how the interaction takes form, so that we are digging a little bit more into the light-matter interaction in a more deep way. So thanks guys for watching, and see you in the next video.